Now, in the last lecture, what we discussed was what happens under a periodic perturbation. And we of course chose t0 to be 0 for convenience. And this v of t started off from a 0 value before t equal to 0. That is why the theta of t is here. Plus a term which depends only on time via the e to the minus I omega t and the e to the I omega t here. F and f dagger are operators which are time independent. And then the first order calculation for ck of t, where k is not equal to I, is straightforward. You just do this integral. The delta ki term of course is 0 here. And once you do the integral, the result is very easy to evaluate. You end up with a function like sine of t times omega ki minus omega by 2 divided by omega ki minus omega by 2. It's a very straightforward result of the integration that we saw in the last lecture. And we wrote this down as square root of this function, which is of course the square of that. This is dt alpha. We write it in this particular fashion because the dt alpha function is going to play an immensely important role in the calculation of the probability of transition to the kth state. However, at this point, let me point out that in writing it this way, I've actually made a small error. Thanks to a student for pointing this out from the last lecture. This error was made in the last lecture also. The point is, square root of a square, for example, square root of x square is not x. Because in calculus square root is always the positive square root, square root of x square is actually mod of x. Since we don't really have the modulus as a result of the integration, replacing the sine omega ki minus omega by 2 into t by omega ki minus omega by 2, which we really had as a result of the integration here, by square root of d actually is not right, because whenever this quantity inside the bracket becomes negative, square root of d is not this thing, but rather it's negative. So this is correct up to a sign. It could be either a plus or a minus depending on whether this thing inside the square bracket is positive or negative. Now, although I do agree that this was an error, it's not going to make things very different in the long run, for the simple reason that, as we will soon see, the major contribution to d comes from a region close to omega ki equal to omega or alpha equals 0, and in this region this function is positive. It becomes negative only outside the central peak, and its value there is really tiny and we don't really care too much about it. So strictly speaking, this is wrong. This replacement of the integral here by the square root is not quite correct. However, for all practical purposes, no problems will come from doing this. Of course, the reason why we wrote this as square root of d here is that when we take the modulus square of this quantity, we get the probability of transition from the state I to the state k, and it's given by this whole expression. Of course, when you square these expressions, it doesn't matter whether it was plus square root of d or minus square root of d to begin with, you get d anyway. So these two terms have no issues. The last term here can acquire either a plus sign or a minus sign. Once again, the minus sign will occur only in a situation where you are far away from the central maximum and the value is too tiny there to be of really any consequence. Just to put this in perspective, let me show you what the graph function dt alpha looks like. Again, we already saw this in the last lecture. This is plotted from t equal to 1, but you could actually plot it for any t, and the height is given by t square and the width is given by 4 pi by t. Beyond that, the function is very tiny, and because it's very tiny, this is where, at least between this minimum here and this next minimum, the function inside the bracket here is actually negative, but it's pretty small, so we don't really bother too much about that sign issue. One thing is clear, that if you make t very small, when you make t very large, the height of this graph becomes very, very big and the width becomes very, very small. So what we are getting here is basically something which looks like a delta function. That's actually supported by the fact that when you do the integration here, you end up with a constant, which, or nearly a constant, is 2 pi t that you get. So 1 by t times dt alpha, this quantity, this integrand, is something which becomes very high and very narrow as time increases, and in the limit of very large t, 1 by t dt alpha is actually delta function, 2 pi delta alpha, because the integral or the area under the curve stays the same as 2 pi. Now this is a result which will be very important when we go on and talk about transitions to continuum states. Armed with this background, what we are going to do now is we are going to discuss transitions to states which are in the continuum. So let us point out that the major problem in this context is usually one which is more due to convention. The normalization for discrete eigenstates of H0 is pretty straightforward. We usually choose them to be orthonormal in the sense that the overlap between phi I and phi j, or the bracket bra phi I ket phi j, is equal to delta ij. That is, it's 1 when I equals j and 0 when I is not equal to j. Now this is almost universally the situation adopted whenever the states are discrete. Now the problem is when the states are continuous, then things are not so clear-cut. So when you have continuum states, different authors tend to use different normalization conditions. So what we will do is we are going to sort of not play favorites, and we are going to use a notation which will take care of all the different authors in one go. So we will accommodate all the different normalization choices that people use simply by saying that the overlap between the continuum states alpha and alpha prime, these, remember, are eigenstates of the unperturbed Hamiltonian, but they are in the continuum. So we expect them to have a delta function, delta of alpha minus alpha prime, because of the orthogonality. But the normalization factor in front, this is where different authors differ in their choices. We are just going to write that as n of alpha. Of course, you might argue that why is it n of alpha and not n of alpha prime, or why not n of both alpha and alpha prime? And the answer is simple. Wherever alpha is not equal to alpha prime, it doesn't matter what the prefactor is, because the whole thing is going to be 0 anyway. So it just makes sense to talk of this as a function of alpha alone. Now different authors choose different values for this function, or different forms for this function. Some authors choose just 1. To them, alpha alpha prime, the overlap is simply the delta function. Some authors choose 2 pi h cross times delta alpha minus alpha prime for the overlap, which means n of alpha is 2 pi h cross. Some other authors, depending on what their major goal is, choose some other form. So we are leaving this particular form open at this stage, some function n of alpha. Once you do this, the resolution of the identity is no longer sum over all the states alpha I ket alpha I bra. It becomes an integral, of course, and the integral is over d alpha by n alpha. That's the measure. So instead of just using the projector alpha ket alpha bra, you have to use alpha ket alpha bra divided by this normalization factor here, n alpha. Now once again, let me warn you that this is still a formal expression. It might so happen that the spectrum of your unperturbed Hamiltonian H0 may have a discrete part and a continuum part, and of course if it has a discrete part, then this will be replaced by a sum over the discrete part and an integral over the continuum part. So that's sort of taken to be understood here. Now just to sort of verify that this really is the resolution of the identity, let me point out that if you start with a state psi, an arbitrary state psi, you should be able to expand this in the eigenbasis provided by alphas. So you can write that as an integral over alpha prime d alpha, that is integral over d alpha prime of the ket alpha prime times some coefficients. These are of course what where the cn's before for the discrete case, or the an's, the coefficients in front of the phi n's. It has now become a function of alpha prime. So instead of a sum over discrete energy eigenstates, you are doing an integration over the continuum. So this much is fine. So how do you find f of alpha prime? Simple. If you take the overlap of the ket psi with the ket alpha, or basically apply the bra alpha on the ket psi, what you end up with, of course, is this integral becomes very simple because of the bra alpha ket alpha prime bracket, which is a delta function, and you end up with n alpha f of alpha. So ket bra alpha ket psi is actually equal to n alpha f of alpha, which means the ket psi itself, if you just take this expression, here I have replaced the alpha prime by alpha. After all, it's a dummy variable of integration, and instead of f of alpha I have written the bracket alpha psi divided by n of alpha, which is of course what this result tells me. So this is what the ket psi is. But then this is also, if you just move the ket from here at the end to the beginning, you can rewrite this as an operator, integral of d alpha ket alpha bra alpha by n alpha acting on the ket psi. This is just the same expression as this. The ket has just moved from here to here. So this is exactly the operator which, acting on the ket psi, gives you ket psi back. And since ket psi is completely arbitrary, this is exactly what the identity operator is. So this verifies our statement that the resolution of the identity changes over to this. Of course, once again, if you read a specific author who uses a particular convention for n alpha, that n alpha will appear in the denominator here. So if somebody uses the Dirac delta function directly as the overlap, chooses that normalization, then of course the n alpha is just 1. Otherwise, you may have 2 pi h crosses or 2 pi's or other factors depending on what choices have been made here. So what is the projection operator for a state around a particular ket alpha? The answer is simply this. If you take states which are very close to ket alpha within the parameter d alpha range, the projector is going to be ket alpha bra alpha times d alpha by n alpha. So this is an infinitesimal projector, of course, because it projects into an infinitesimal range of alpha values. And we can write this d alpha by n alpha as a measure d phi. Of course, we could have done that in the last integral as well. So what is the probability of transitions to states near alpha? Well, all you need to do is apply this projector on the state psi, and that will give you the probability amplitude, and then you take the mod square and you end up with this result, alpha psi mod square d phi. Just to verify that this works, let's check whether if you integrate dp alpha, this infinitesimal probability of finding the system in a set of very close eigenstates parameterized by the eigenvalue range alpha to alpha plus d alpha. If this is correct, then if you integrate this over all possible values of alpha, which means all possible, integrate over this d phi measure, you should get 1. Let's check whether you do get 1. Well, alpha psi mod square is of course this, and then you just use the fact that ket alpha bra alpha by n alpha integrated over d alpha, this is of course the same as this thing, and this thing in the middle here is nothing but a resolution of the identity. So this is nothing but the overlap of psi with itself, and since psi is normalized, this has to be 1. So this checks out that we are right in saying that the probability of finding the system in a range of states, in a narrow range of states, in a window characterized by central value of alpha, and essentially with where labels go from alpha to alpha plus d alpha, is given by this quantity. Now comes our question about this what does time-dependent perturbation theory say about transitions from a state I to a state around alpha, where alpha is, we have taken epsilon alpha to be greater than epsilon I just for convenience. Now, if you go back and take a look at, we have to go back quite a way and take a look at this expression. Here you have three terms, but notice that if omega is close to omega ki, that is epsilon k minus epsilon I by h cross, then this term is going to dominate over the other two and we can safely ignore the other two. So that is what we mean when we say we are ignoring non-resonant terms. I'm not claiming that we are exactly at resonance or omega is exactly equal to omega ki, but when omega is close to omega ki, this term is much bigger than these two other terms. That's what we are going to use here. Just to point out that that is simply something which follows from the fact that this d function is rather narrow and becomes narrower and narrower as time increases. So a d centered around omega around 0, where omega ki is almost equal to omega, is really close to its peak, whereas at the same value of omega, omega ki plus omega has a rather large value of alpha, which means it's pretty far away, and so the value is very close to 0. So coming back to our particular thing here, so when we want to calculate the probability of transition from the state I to a state around alpha, if we ignore the non-resonant terms, we end up with dp alpha given by 1 by h cross square. Just the first term is picked off, alpha fi mod square dt omega alpha I minus omega d phi. So this is just the term that you get when you take the probability expression that we had and just use the resonant term, that is where omega alpha I minus omega is being considered. Now remember that for large t, dt omega alpha I minus omega, or in this case dt for any second argument alpha, essentially behaves like the delta function except that there is an extra t in front. So there is 2 pi t delta alpha. This is what dt alpha becomes for very large values of t. So for very large values of t, this quantity dt omega alpha I minus omega, which is sitting here, over t simply becomes 2 pi delta of omega alpha I minus omega. Now just remember that omega alpha I minus omega is nothing but epsilon alpha minus epsilon I by h cross minus h cross omega, this whole thing, or minus omega. So when you bring this in the numerator, it becomes minus h cross omega here. So this is what d of t omega alpha I minus omega behaves like for large t, just like a delta function. Now, using the basic properties of delta functions, you can replace the argument of the delta function with this energy conservation term, epsilon alpha minus epsilon I minus h cross omega, at the expense of a 1 over 1 by h cross, which means by putting in an extra h cross here. So finally, the probability of transition to a bunch of states close to alpha is simply what you get when you take this expression and replace this dt omega alpha I minus omega with t times this delta function, and because of this h cross square which was already here, you end up with 2 pi by h cross, that's this 2 pi h cross by h cross square. The alpha fi mod square comes in, and then you have an energy conserving delta function times d phi. What is important is that there is a t in front. So that means the probability of transition to a bunch of states close to alpha keeps on increasing linearly with time. The transition probability per unit time interval is what you get when you divide this dp alpha by t. So this is our final result. Instead of going from a state I to some arbitrary state alpha, of course this is still arbitrary, all I'm doing is changing the notation a bit. I'm saying that you're going from I to a state f, from initial to final, and we are calling this dwfi. So this dwfi is essentially dw I to f, and that works out with 2 pi by h cross f fi mod square, that's the matrix element that you had in front, mod squared, times the energy conserving delta function times this measure d phi. d phi, remember, is d alpha by n alpha. So this is one of the most important rules in time-dependent perturbation theory. In fact, this is the most important rule not only in time-dependent perturbation theory, it's one of the most important rules in all of quantum mechanics. It is so important that it's even called the golden rule. This is called the Fermi golden rule, after Enrico Fermi, of course. Now, let's try to understand this rule a bit. The delta function here, of course, imposes energy conservation. Notice that here we are not really talking about photons, because there is no electromagnetic radiation at this stage. It's just the rate at which the frequency of the at which the perturbation changes with time, this omega here. But this result looks very much like the energy transition from epsilon I to epsilon f occurs because somewhere an energy quantum of the order h cross omega is created. And we will later see that this is actually quite close to reality. Okay, of course, this result was for the situation where epsilon I was more than epsilon f. But if epsilon I were less than epsilon f, the thing that we discussed was epsilon f, the final energy was more. If the final energy is less, then epsilon I minus epsilon f close to h cross omega will give you the other resonant term, which is the second term in our pi to k expression that we wrote down earlier. And if you use that, the second term dominates, and we have a very similar expression in the end. You should try working it out yourself. You will see that almost everything stays the same, except that instead of the energy conserving delta function having an argument epsilon f minus epsilon I minus h cross omega, the argument here will be epsilon I minus epsilon f minus h cross omega. So that's a very small minor change here. Now this formula looks like it depends on normalization, the convention that we use, because d phi after all is d alpha by n alpha. But you have to realize that if fi involves the state f which is in the continuum, and the normalization of that state f is also controlled by the same factor n alpha. In fact, the square here produces exactly the same factor n alpha, which cancels the 1 by n alpha here. So ultimately, no matter which normalization you use, you end up with the same expression for dwfi. This result here is independent of the particular normalization used. And one more important thing, we said that this gives us the probability per unit time of transitions to a bunch of states close to the final state f, where close essentially, how close is essentially in denoted here within the d phi. D phi involves d alpha, the eigenvalue range which labels the final states. Now, of course, all of these states should ultimately end up having an energy epsilon f, which is given by epsilon I plus h cross omega, because for all other energies, this thing is 0. So what we can do is we can eliminate the delta function by integrating over the energy and obtain a result which looks different but which essentially means the same thing. So you must realize that alpha, the eigenvalue which labels the state, of course one of the labels has to be the energy epsilon, but that cannot completely label the state in all cases. There would be other parameters beta. And so this d phi that we have written down, which is actually d alpha by n alpha, should be expressible in this form: d epsilon for the energy range times variation in the other parameters d beta times a function of epsilon and beta will be called density of states. This tells us essentially how many states are there in the range between epsilon and epsilon plus d epsilon, beta and beta plus d beta. And if we plug this form d phi in here and integrate over all energy, what happens is the energy term, the integral d alpha, d epsilon, trivially drops off. But what it does, what the delta function does, is that it forces epsilon f to be equal to epsilon I plus h cross omega for all the states, which means the Fermi golden rule now takes the form dwfi is 2 pi by h cross ffi mod square times the epsilon has already been integrated out over, but you still have the d beta integral to do. So now we are talking of bunch of states all with energy epsilon I plus h cross omega, but with other labels varying over the range beta to beta plus d beta, and we are asking what is the probability of transition to those states. And notice that the density of states comes in a big way here, but you have to remember that the density of states depends on both the energy and the other parameters. In this case, the energy epsilon f is fixed at epsilon I plus h cross omega. That is what the energy conserving delta function does for you. So this is the other form of the Fermi golden rule, where we have already integrated out over the energy, and this form is actually quite useful. How useful we will see in the next few lectures. Armed with the Fermi golden rule, what we will do in the next lecture is we will discuss the interaction of light with matter. In particular, we will be discussing the semi-classical theory of light-matter interaction. Now, what does the word semi-classical mean in this context? It simply means that we are going to treat the atoms or matter involved using quantum mechanics, but at the same time treat the light coming in as an external classical electromagnetic field. Now this means that we are not going to consider radiation as quantized, hence no photons. It so turns out that almost all phenomena in light-matter interaction can be described within this approximation with an additional small consideration as far as the vacuum fluctuations are concerned. We will talk about that later. But it so turns out, and this may be very counterintuitive based on the fact that the very development of quantum mechanics was through the photon. As I was saying, it so turns out that for 99% of the phenomena involved in light-matter interaction, you do not really need the photon. You actually need the photon for a very small subclass of phenomena, and that actually constitutes the subject of quantum optics, which we will not consider in this series of lectures. In the next lecture, we are going to use the semi-classical theory to understand radiation caused by atoms, absorption of radiation as well as emission of radiation. We will also see that you cannot describe, say spontaneous emission this way, so we will need to modify the theory a bit. But all that will be covered in the next lecture. Bye till then.